In this video, we will discuss strain energy in bending. Let us assume a beam of length L subjected to a bending moment M. Because of this bending moment, this beam will take a form of circular arc. Let us assume that this arc is making an angle theta at the center with radius r. From the arc by radius formula, you can see we will get 1 by r is equal to theta by L. We also know from the bending equation m by I is equal to sigma upon y is equal to E by r. In this equation, in place of 1 by r, write theta by L, then you will get equation m by I is equal to E theta by L. So in place of 1 by r, I have written theta by L. Further, we can rewrite this as theta is equal to ml upon EI. Now in this equation, you can see that this length of beam, Young's modulus of this beam material, and moment of inertia of cross section of this beam, these three elements are constant and therefore theta is directly proportional to m. So if you plot applied bending moment and theta in a graph, you will get a plot like this. So here in y-axis I have taken bending moment and in x-axis I have taken angle theta. When this bending moment is gradually increased from 0 to a particular value m, so bending moment is increased from 0 to m, then this angle theta will start its value from 0 to a particular value theta. During this bending of this beam, some work has been done by this bending moment, and that work is equal to bending moment into angle. This bending moment into angle. But this bending moment is varying from 0 to a maximum value of m. So average bending moment will be half m. So this is what I have written, average bending moment half m into this angle theta, and this is actually this area. Now this work done is stored in the beam in the form of strain energy. So strain energy is half m into theta. Now you can rewrite this equation in different forms. Here m and theta are there, so either you can replace m by theta EI upon L, or you can replace theta by ML upon EI. So first replace theta by ML upon EI. So you will get this equation m square L divided by 2 EI. And if you replace m by theta EI by L, then you will get strain energy as EI theta square divided by 2L. These two equations holds good as long as this bending moment is constant throughout the length of this beam. But if this bending moment is varying at different sections, in that case what we will do, we will take a very small length of this beam and we will determine strain energy of that small portion, and then we integrate throughout this length. In that case, this equation will become m square dx divided by 2 EI. Here dx is the length of that small element and mx is the bending moment at that small element. So in that way you can determine strain energy when bending moment is varying. Most of the cases bending moment may not be same in throughout the length. So we will take two examples where bending moment is changing. So we will use this formula to determine the strain energy of the beam. So first problem is, taking into account only the effect of normal stresses, determine the strain energy of the prismatic beam AB for the loading shown. Here this beam is a cantilever beam fixed at one end at A and free at B. It is subjected to a uniformly distributed load of W per unit length. Total length is L. So what we will do, so formula for strain energy will be integration of mx square dx upon 2 EI. So what we have to do, from free end we will take a small length dx. Here small length dx we have taken at a distance of x. At this section we have to determine bending moment, which is mx. So mx is equal to, for this length, load is this w per unit length. So length is x, wx, which will be applied at the center. So its distance from this section will be wx multiplied by x by 2. So wx into x by 2 is wx square by 2. So this is the bending moment. Now put this bending moment here in this equation and integrate from 0 to L, because this x is varying from 0 to this maximum length L. In place of mx, I have written wx square by 2, wx square by 2, it's a square, mx square into dx divided by 2ei. This 2 square I have taken out, and this 2ei, these are constants, so you can take this out. So 2 square is 4 into 2 8ei, so 1 upon 8ei I have taken out. Wx square whole square dx, this integration you have to do. Now w is also constant, so you take it out. So w square upon 8ei, and what you are getting is 0 to L x raised to 4 x raised to 4 into dx. So its integration is very simple. So x raised to 5 divided by 5. So what you will get, L raised to 5 divided by 5. So 1 is 0, 1 is L. So this is what you will get. Strain energy of cantilever beam subjected to uniformly distributed load W. From this formula you can calculate strain energy of a cantilever beam subjected to uniformly distributed load. Another example I have taken is a simply supported beam, again subjected to uniformly distributed load of W per unit length. The length of the beam is capital L. Again same formula, mx square dx upon 2ei. Now in this case you have to determine reactions either at A or B. So I have taken, I determined reaction at B. Now you can see that this load is W per unit length for entire length. So total load is W into L, which will be acted at the center, at the centroid, or so it will be shared by both A and B equally. So this resultant will be WL divided by 2. So here what you will get, one reaction upward direction which is equal to WL by 2. Again you have to take one section at a distance of x. So at this section you have to determine bending moment. So bending moment, there are two forces. One is upward force because of this reaction, which is equal to WL by 2, and another one is same which we have discussed just before, WX square by 2. So mx will equal to WL by 2 into x. So WL by 2 into x, this distance, and another one downward force, because of downward force, negative WX square by 2. So this is mx. Now put this value here in this equation. So this whole square dx. Now here you can see W by 2 in both sides. We can take it out. So square is there. So W square by 4 will come out. So W square by 4 to the 8. So W square divided by 8ei. So what is left? What left is Lx minus x square. So Lx minus x square whole square. And now simplify this. A square a minus b square. So what you are getting, Lx square a square plus b square x raised to 4 minus 2 times Lx into x square. So that will become 2Lx cube. Now integrate this separately. So first term Lx square, so Lx square 0 to L dx. Second one x raised to 4 0 to L minus 0 to L 2L x cube dx. If you integrate this, here you can see L square is there and it will become x square. So its integration x cube by 3. So x cube will become L cube by 3. So L cube into L square, it will become L raised to 5 divided by 3 plus L raised to 5 divided by 5. In this case, second one, L raised to 5 divided by 5 minus this will become x raised to 4 by 4. So 2 to the 4. So at numerator it will become L raised to 5 divided by 2. So now L raised to 5 you can take it out and simplify this. So what you will get, 10 plus 6, 16 minus 15, 1 by 30. When you solve this, you will get strain energy as W square L raised to 5 divided by 240 EI. So a simply supported beam which is subjected to uniformly distributed load, you will get strain energy as W square L raised to 5 divided by 240 EI. In this way, you can determine strain energy of beam subjected to different kinds of load having different bending moments at different sections. Thank you for watching this video.